Let me take an example. I will consider a simple circuit, okay, but it can be anything. This is the circuit given to me. So, let us say this is V naught and this is R, 2R, R and R, and I want to model it at these two terminals. Again, I want to emphasize that this equivalence is valid for the voltage and current at these two terminals, nothing else. Okay. So, it says that if you connect this circuit or its model to any circuit you want, then the behavior will be exactly the same at these two terminals and also inside the circuit that you connect to it. Okay. So, now I have to find the Thevenin voltage, and for that all I need to do is do not connect anything between 1 and 1 prime and find the voltage across it. In this particular case, I have chosen the value, so that it is very easy for me to calculate, okay, because looking here I have a series combination of R and R, which gives me 2R. Okay. So, this is 2R, and looking here I have 2R parallel to R. So, I have R. So, effectively between V naught and this point I have R and R. So, the voltage that appears here will be V naught by 2. Okay. And between that point and here again I have R and R. So, the voltage that appears here will be V naught by 4. So, my Thevenin voltage VTH will simply be V naught by 4. Then I have to calculate RTH. For that, what I have to do is I have to set this voltage to 0. So, I short circuit it and I have R, to R, R and R. Okay. Again 1 and 1 prime. So, by the way, I measured VTH with this polarity. Okay. So, that is V naught by 4. If I had taken the opposite polarity, it would have been minus V naught by 4. Now, I have to look back and calculate the resistance. I can apply a test voltage and find the current, but in this case it is a simple combination of resistors. So, it is quite easy to do. What I will do is look here, I have 2R parallel R, which gives me 2R by 3, and here I have that 2R by 3 in series with R, which gives me 5R by 3, and finally, here I have 5R by 3 in parallel with R, which gives me 5R by 8. Okay. So, the Thevenin resistance is 5R by 8. Okay. So, the equivalent circuit would simply be V naught by 4 in series with resistance 5R by 8, and this is 1 and this is 1 prime, that comes from the polarity with which I measured VTH. Okay. So, this is 1, that is 1 prime. Now, if you are given specific values, so let us say V naught was 8 volts and R was 16 kilo ohms, okay, then this would be 2 volts. The next to this 5R by 8 would be 10 kilo ohms. Okay. And you can do this for any circuit that you want. Now, if the circuit is more complicated, the procedure to find the voltage and the resistance may be little more laborious, but the principle is exactly the same. Okay. We can consider another example, this time including control sources. I have a voltage source here and I have this 1 kilo ohm resistor. The current through 1 kilo ohm resistor is I x, and this current controlled voltage source is 1 kilo ohm times I x. Okay. Procedure is exactly the same as before. What I want to find, of course, is the equivalent of this between the terminals 1 and 1 prime with the voltage source value V t h and the resistance value R t h. Now, to find the voltage V t h, all I have to do is do not connect anything to 1 and 1 prime and find the voltage between these. Okay. So, that is I have to find the voltage over there, and that I know that the drop here is 1 kilo ohm times I x, and the drop here is also 1 kilo ohm times I x, because I x is flowing through the 1 kilo ohm resistor. So, V t h will be 1 kilo ohm times I x, because this drop is exactly the same as that, and applying KVL around this loop, we have minus 10 volts equals 1 kilo ohm times I x, which is the drop across the resistor, plus 1 kilo ohm times I x, which is the drop across the current controlled voltage source. Okay. This is equal to 2 kilo ohm times I x, and solving these two, we easily see that V t h is minus 5 volts. Deliberately, I took a case where V t h comes out negative. Okay. The polarity is quite important. We are measuring the voltage between 1 and 1 prime, with 1 being positive and it comes out negative. So, in this particular case, V t h will be minus 5 volts. Okay. And to calculate R t h, I have to take this circuit, disable the independent sources, but retain the dependent sources exactly as they are. Okay. So, I short the 10 volt independent source, and I have 1 kilo ohm here. I x is defined exactly the same way as before, and this voltage is 1 kilo ohm times I x. Okay. And I want to find the impedance looking in that way. Okay. Now, because I have a current controlled voltage source over here, so let me apply a test current I test and see what voltage is developed across this. Okay. Now, I know that this V test equals 1 kilo ohm times I x. I do not yet know what I x is. Okay. Now, I also know that this V test is also the voltage between these 2 points, and that voltage drop, considering the direction of I x, is minus I x times 1 kilo ohm. Okay. So, V test is also equal to minus 1 kilo ohm times I x. Okay. So, by adding these two, V test will come out to be 0, independently of I test. Okay. So, that means that the Thevenin resistance, which is V test divided by I test, will be equal to 0 ohm. Okay. So, again this is a little weird case, but because the output is across the current controlled voltage source, you expect that you see a 0 ohm resistance. Okay. So, we have R t h to be 0 ohms. Okay. So, this is 0 ohm and the circuit in fact acts like an ideal minus 5 volt voltage source between 1 and 1 prime. Okay. So, if this were a resistor, you would have got some resistance in series with it, but this is a current control voltage source. So, the resistance looking back this way happens to be 0. Okay. But again, what I want to highlight here is that the procedure is very systematic. You open circuit the output, find the open circuit voltage and you null all the independent sources in the circuit and determine the Thevenin resistance RTH.